Hello and welcome to this presentation related to integration applications, where we're going to analyse centres of area, also termed centroids. The centroid is shown in this diagram here, which relates to the area under this curve. It's defined by its y-bar position, that's the vertical distance from the x-axis to the centroid, which we'll show in a moment is calculated by this formula, and the x-bar, that's the horizontal distance from the y-axis to the centroid of area. For your reference, there is a previous lecture associated to the calculation of centroids of simple sections like the I-section beam shown here, in which we outline the concept of the first moment of area. This is a recap slide from that presentation. As the first moment of area is a quantity we require to calculate when determining the centroid position. So you may want to review this initial presentation for basic concepts of centroids and basic terminology before continuing with the current presentation. Here's a presentation overview. We commence by defining what's termed the first area moment, or first moment of area, a property we need when calculating the centroid locations. Then we derive a formula for y-bar, shown here, and derive the formula for x-bar, shown here. To define the centroid location, shown here on our sketch, we need to calculate the x-bar location, that's the horizontal distance from the y-axis, our datum in this case, and calculate the y-bar, that's the vertical distance from the horizontal datum axis in this case. And here are the approximate start times related to the various sections shown on this slide, hopefully to aid your ease of access through the presentation. Presentation overview continued. Then we have example 1C, where we have to find the centre of area, shown here on our sketch, between the curve y is equal to x squared minus 9, plotted here, and the x-axis here. The full work solution for this example is shown. In example 1C commences approximately 8.5 minutes into the presentation. Presentation overview continued. Then we have a series of questions, question 1C, question 2C and 3C. You can attempt these at your own pace, although full work solutions are shown. Here are the approximate start times for questions 1C through to 3C. Please note these are only approximate start times though. Presentation overview continued. And we have question 4C and 5C. And here are the approximate start times for questions 4C and 5C. So introduction here to centroids. To define a centroid, we need to calculate the x-bar location and the y-bar location. Let's firstly define the first moment of area about a fixed axis of a laminar two-dimensional shape that has area A and a perpendicular distance y from the centroid of the laminar is calculated from the formula area A multiplied by perpendicular distance y. So generically speaking, the centroid location is the first moment of area about a datum axis divided by the area of the laminar, or the area of the section considered. That's a generic formula we'll be using to calculate the x-bar and y-bar locations. Let's first consider the calculation of the y-bar location, shown here on the diagram. So initially let's consider the first moment of area, or first area moment, of the element, shown shaded in the sketch. This is the elemental strip shown here. And we're calculating the first area moment about the OX axis, the horizontal axis, this axis here. So to calculate the first area moment, it's simply the area of the strip multiplied by its centroid location from the OX axis. So from the sketch, figure 6, the area of our elemental strip is the height y, shown here, multiplied by the thickness dx, shown here. And remember from our previous presentations related to integration, this elemental strip is very thin. Consider dx to be so thin it cannot be measured. Therefore, although it's a rectangle, the heights at the left-hand side and right-hand side of the rectangle are assumed to be the same because the thickness dx is so thin. The centroid location of the elemental strip, which is obviously half the height, is y upon 2, shown here. So evaluating the above, our first area moment is a half y squared dx. And we need to calculate the first area moment of the area under this entire section, shown here. So the first area moment of the whole section about OX between our limits of the origin and B is given by this integral here. We're integrating the first area moment between the limits of 0 and B. So here's our formula derived for the elemental strip. Just note on the next line, I've simply taken a constant of a half outside of the integral. That leaves me with y squared integrated with respect to x between our given limits. So the calculation of the y bar location is given by this formula, the first moment of area divided by the calculation of the area between our limits, and the area of our elemental strip was simply y dx, height multiplied by the width, but between the same limits, of course. So that's the generic formula for calculating y bar. Let's now consider calculation of the x bar, this location here on our diagram. So once again we consider calculating the first area moment of the elemental strip, but this time about the OY axis, this axis shown here. So the first moment of area about the OY axis is again the area of the elemental strip. So that's again y dx, but this time multiplied by dimension x, this horizontal dimension here. So evaluating the first area moment, that can be written as xy dx, x times y times dx. So the first area moment of the whole section about the OY axis between our limits of O and B, written here, first area moment, so our integral shown here, and we know from above that's xy dx. So calculation of the x bar location, formula for x bar is the first area moment divided by the area of the section. Let's consider an example, example 1c shown here. We've got to find the position of the centre of area, the centroid, between our curve y equals x squared minus 9. That's plotted here in figure 7, and the x-axis shown here. So in other words, this is the area we're considering. So the first thing we'll do is calculate the area A, using our standard integral here, integrating the function y with respect to x between the limits of 0 and b. In this case we're integrating x squared minus 9, that's our function of x, with respect to x between the limits of 0 and 3. Here's our 0, here's our 3, the range of x in this case. Your standard forms to integrate, so x squared becomes x to the 3 upon 3, and minus 9 integrated becomes minus 9x. Here's our limits on the rear of the square bracket here, and imposing the limits for x, upper limit is 3 for x shown here, imposing the lower limit for x in our square bracket here, then on evaluating that will become 0, So we can determine in this case the area enclosed between y is equal to x squared minus 9 and the x-axis is negative 18. Example 1c, solution continued. So let's now calculate the first area moment about the x-axis. Here's the first area moment formula we derived on our previous slide. When calculating the first area moment about the x-axis, remember it's y squared multiplied by dx. So here's our y function, the x squared minus 9, but we must square the bracket this time. And that's what's shown here, y squared. Our limits again will be 0 and 3. Again, these are standard forms here. Integrating x to the 4 with respect to x becomes x to the 5 upon 5. The negative 18x squared becomes negative 18x cubed upon 3. And positive 81 integrated with respect to x becomes positive 81x. Our limits now applied to the rear of the square bracket. And next we simply impose the limits, so the upper limit of 3, replacing an x. And again inserting the lower limit of 0 for x, all the terms will become 0. So we've evaluated now the first area moment about the x-axis. It's 64.8. So we can now calculate the y bar. It's the first area moment divided by the cross-sectional area, which we calculated to be negative 18, shown here. So the y bar is negative 3.6 units. So negative 3.6 on the y is the location of the y bar, but of course to define the centroid of this area under the curve, we need to calculate the x bar, which we will undertake on the following slide. So example 1c, solution continued. Now we're determining the first area moment about the y-axis, vertical axis here. Again, we know from our previous derivation, the first area moment about the y-axis is given with this formula. Inserting y into the formula, and multiplying y by the x, shown here. Our limits again for x are 0 and 3, so we're integrating with respect to x. And again we have standard form inside the bracket, both terms of the form x to the n, so integrating x cubed with respect to x becomes x to the 4 upon 4, and the negative 9x integrated with respect to x, negative 9x squared upon 2, limits of 0 and 3. Inserting the upper limit of 3 again wherever I see an x, and again the lower limit when inserted of 0 will cause the square bracket to become 0. Need to be careful because that's not always the case, but it is in this particular example. And then evaluating the first area moment about the y-axis is negative 20 and a quarter, or negative 20.25 in decimal. So finally, to calculate the x bar, it's the first area moment again divided by the area, and that evaluates to 1.125 units, shown here on our diagram. So now we have the y bar and the x bar, we can define the centroid location. So there's the full work solution for example 1c to find the x bar and y bar for the lamina or the section given. Example 1c, solution continued. I've just shown a larger diagram of the location of the y bar and the x bar, purely for reference. Let's now consider some questions from our workbook. Question 1c here. We're asked to find the centroid of area bounded by the curve y is equal to 3x plus 2 and the x-axis. We're given the range of x from x is equal to 0 to x is equal to 4. Answers for the x bar and y bar shown here. Here are the respective formulae for calculating y bar and x bar we derived previously, which you'll need to use to solve question 1c. Just note in this case you can actually find the area of the section without using integration. It's just the area of a trapezium actually. But anyway, I would encourage you to stop the presentation and attempt question 1c, although the full work solution is shown on the following slides. Question 1c is the commencement of the solution. Initially I've sketched the shape we're considering. So for the y function given in the question, y is equal to 3x plus 2, which is essentially a linear line shown here. We've got to find the area under this line that's bounded by the x-axis shown here. So the limits of the integration process are given here, x equal to 0, x equal to 4. And we need to calculate both the x bar and the y bar. Remember, the x bar is measured from the vertical y-axis and the y bar is measured from the horizontal x-axis. See here I've calculated the area using our standard formula of base multiplied by mean height. That's how we calculate the area of a trapezium, which is the shape we have here. So the base in this case is 4 units on the horizontal axis, and the mean height is calculated from the maximum height, which is actually 14 up here, calculating our table here when x is equal to 4, y is equal to 14, and 2 here, when x is equal to 0, y is equal to 2. So that's how I calculate my mean height, 14 plus 2 divided by 2. So evaluating the area is 32. Question 1c, solution continued. And calculate the x bar first of all here. So here's the formula for calculating x bar. It's the first moment of area about the vertical axis. Notice our limits are 0 and 4 for the integration process. And although I've calculated the area from standard formulas on the previous slide, just for the practice of integrating, I'm actually going to calculate the area here using the y dx integral. And the limits are the same. So you'll see when evaluating the integral in the denominator, we will get the value of 32, which we calculated previously from our standard formula. I'm going to let you work through the solutions here. I've laboured the solutions for you. Sorry, they're handwritten here. I just haven't had a chance to type them up. But hopefully you can follow them through at your own pace. The first area moment will calculate to be 80. The area is 32. So the x bar calculates to be 2.5 units. That's this value here. Question 1c, solution continued. Now we're going to evaluate y bar. Again, using our standard formula. Here's the first area moment about the x-axis. Standard formula. Limits 0 and 4 in this case. And again, I have shown the integral for calculating the area here, which of course will be 32. As we're calculating the y bar, don't forget we have to square the y function. So that's binomial expansion shown here, evaluated here. All terms standard form. So integrated with our ax to the n function shown here. Question 1c, solution continued. And here I've labelled the evaluation, inserting my upper limit of 4 for x. Again, inserting the lower limit of 0 means all the terms become 0. And finally, we show that y bar is equal to 4.75. Y bar shown here. So finally, we've calculated the centroid location in terms of x bar, 2.5, and now y bar, 4.75. No units have been stated in this particular question. So here's the centroid position. Question 2c, we've got to calculate the position of the centroid for the area that's bounded by the curve y is equal to 5x squared and the x-axis. We're given the limits of the area in terms of x is equal to 1 and x is equal to 4. Answers for x bar and y bar shown here in the bracket. Again, I would encourage you to stop the presentation and attempt exercise 2c. Here again are the formulae for calculating x bar and y bar. Full work solutions shown on the following slides. Question 2c, commencement of the solution. Just plotted out the curve here. This is y is equal to 5x squared between the limits of x equal to 1 and x equal to 4. So we have to calculate the x bar and the y bar locations to the centroid of the section under the curve y is equal to 5x squared. Question 2, solution continued. Firstly, calculate the x bar. I'm going to let you review this solution at your own pace. Again, my handwritten calculations, unfortunately, but the solution is quite well laboured here, so hopefully you can follow each step through the process. X bar calculates to be 3.036. Again, no unit is stated in the question. Question 2c, solution continued. Part 2 here, we're calculating the y bar. Always remember when calculating the y bar, it is the y function squared. So using the laws of indices here, so that will become 25x to the power of 4 here. Again, I'll let you review the solution at your own pace. Question 2c, solution continued. Y bar evaluates to 24.36. So now we've determined both x bar and y bar for the section given in question 2c. As question 3c, we've got to determine the position of the centroid of a sheet of metal, which is formed by the curve y is equal to 4x minus x squared, and we're informed that this area lies above the x-axis. Here's the x bar and y bar locations. Slight complication with this particular question is that we do not have the limits of the integration process, so the first thing we'll do is try and find the limits. Once we have the limits, we'll be able to then, as in the previous questions, determine the x bar and y bar locations. Full work solution is shown on the following slides. So question 3c. So from the question I'm given the function of y. I've rewritten it in this form in the ax squared plus bx plus c format of a quadratic. So by inspection of the given equation, we can clearly see that a is equal to -1. From our previous work related to quadratic forms, that's actually a hat shape. And here's the recap slide showing a bucket shape for our quadratic curve shape and the hat shape for the quadratic curve. We can see that b is +4 and c in this case is 0. That's the intercept. Again, from our previous presentation, we've calculated the vertex, that's the turning point, in both its x and y dimensions. The formula for calculating the x dimension of the vertex is shown here, of -b divided by 2a. If we insert the values, we find the x vertex location is 2, and putting the 2 back into the original equation given in the question, y dimension to the vertex is 4. So essentially here we know that the shape is like a hat, so the vertex is a maximum occurring at x equal to 2, y is equal to 4. What we do not know is the range over which to integrate, so that's the next step in the process. Question 3c, solution continued. So now we're going to find the range of x. To do that, we'll need to factorize the quadratic. Now here's the quadratic equation given. Using our factorization process, again this refers to a previous presentation where we factorized quadratics. We can deduce that our factors are x plus 0 and also minus x plus 4. So that allows us to calculate the roots, and the roots will be x is equal to 0 and x is equal to 4. Again, for your reference, there is a separate presentation on how to factorize quadratic equations. Question 3c, solution continued. So here's a sketch of our section, of which we've got to determine the centroid. So this is y is equal to -x squared plus 4x, and the centroid is bounded by the x-axis. And as shown on the previous slide, our limits are 0 and 4. So as for all the previous questions, we now need to calculate x bar and y bar. And we'll do so on the following slides. Question 3c, solution continued. Firstly, we're going to calculate x bar using our standard formula, calculate an x bar. Our limits here, of course, are 0 and 4 as derived on the previous slide. I'll let you work through the solution at your own pace. For x bar, you should find the value is 2 units. Again, no dimension stated here. And exercise 3c, solution continued. Here's the calculation for y bar. As always, don't forget we have to square the y term, as shown here. The y bar evaluates to 1.6. Question 4c, we've got to find the coordinates of the centroid of area. This lies between the curve y upon x is equal to x minus 2 and the x-axis. This solution is similar to that of question 3c. We obviously need to determine the shape we're considering here and the range over which we need to integrate. So that will be our starting point for the question. Once we've defined the shape, we can then calculate the x bar and the y bar. Just note you'll need to rearrange this equation given in the question for y to commence the problem. This will produce a quadratic equation which we can interrogate to find whether it's a bucket or a hat and roughly where the vertex will be. And then we can factorize to find the limits of the integration process in the x-axis. The full work solution is shown on the following slides. So question 4c, beginning of the solution. So given the equation in the question, it's actually y divided by x is equal to x minus 2. We multiply throughout by x to form the equation y is equal to x squared minus 2x. This is of the form y equals ax squared plus bx plus c, where this time the a in our equation is positive 1, so that makes it a bucket shape. The b in our equation is negative 2. C value is 0 in this case. Again, if we want to, we can find the vertex position. The x dimension for the vertex calculates to be 1 here. The y dimension for the vertex is negative 1. Question 4c, solution continued. Now we're factorizing the x squared minus 2x. So our factors are x minus 2 and x plus 0. So our roots become x is equal to 2 and x is equal to 0. Question 4c, solution continued. So here's a sketch of our curve, y is equal to x squared minus 2x. The curve shown here. And it's bounded by the x-axis from 0 to 2. As always, we have to calculate the location of the centroid, so we need to calculate the x bar, which will be positive value, and the y bar, which viewing the sketch here will be a negative value. This is the centroid, of course. Question 4c, solution continued. So we calculate the x bar here, same way as usual. X bar calculates to be a value of 1. Question 4c, solution continued. And then we calculate the y bar. Again, as always, noting the y squared for the binomial bracket expansion here, shown here. Question 4c, solution continued. Continuing to calculate y bar, and it evaluates to negative 0.4. We expect it to be negative from our sketch because the area is below the x-axis. So now we've calculated the location of the centroid in both the x bar and y bar sense. Here's question 5c. We're asked to sketch the curve y squared is equal to 9x between the limits of x equals 0 and x is equal to 4. We've then got to determine the position of the centroid of this area. The value of x bar stated here, and note the value of y bar is 0 in this case. This is a more complicated question. What we will need to do within the solution is to initially square root both sides to find the equation for y. What will be noted is that for every x value, there actually are a positive and a negative y value. So you'll see that the area we're considering is actually symmetrical about the x-axis, hence the y bar being 0. But anyway, I would encourage you to attempt question 5c, see if you can actually sketch the section being considered here and calculate the x bar. I will show the full worked solution on the following slides. Question 5 is the commencement of the solution. We need to be careful with this equation. It's given as y squared is equal to 9x. We have our limits of x is equal to 0, x is equal to 4. So given y squared is equal to 9x, then obviously y is equal to the square root of 9x, which is equal to 3 multiplied x to the power of a half. 3 multiplied by the square root of x. But we need to be careful, because if y squared is equal to 9x, then transposing for x is actually equal to y squared divided by 9. So this actually means that for each value of x, there actually are two values of y. Let's just think this through for a moment. So we need to be careful because we have positive and negative y inside our bracket here. So obviously if y is equal to 0, then x would equal to 0. But think if y is equal to 1, 1 squared is 1 divided by 9, that's 1 upon 9. But if y was negative 1, we would be squaring a negative 1 to get positive 1 upon 9. So having y of a positive or negative 1 value, we still get 1 upon 9 in the x. So what that's indicating is that when we plot x on a horizontal axis 1 upon 9, we actually have to plot two y values, a positive 1 and a negative 1. And the same occurs when y is equal to positive 2, we will get 4 upon 9, but also when y is negative 2, we still get 4 upon 9. So again, if we plotted it 4 upon 9 on the x-axis, we will plot a positive y and a negative y. So we start to see that this shape given here is located above and below the x-axis. And the same is true for other y values. We have a single x value. Question 5c, solution continued. So firstly we calculate the x bar from our standard formula. X bar evaluates to be 2.4 units. So question 5c, solution continued. So if we plot our equation, y is equal to 3 multiplied by the square root of x, or y is equal to 3 multiplied by x to the power of a half. This is the shape we're plotting, so we can see we have area above and below the x-axis here. So clearly by inspection, the centroid will lie on the x-axis. So that means due to symmetry about the x-axis, the y value must be 0 in this case. So we only need to calculate the x bar value. I would encourage you to stop the presentation and just think through this slide for your own reference. Understand that for each value of x, there actually are two values of y, and that's why we have the symmetrical shape about the x-axis. Here's the bibliography used to help generate the presentation. A very good mathematical textbook for technician engineers. And thank you for viewing.